Welcome to the first video of section 4.2, where we'll be talking about the expected value and standard deviation. The expected value of an experiment is often referred to as the long-term average, or the mean. That means if you keep doing your experiment over and over and over again, you would expect to end up with the expected value of the experiment. For instance, if we toss a coin 10 times, we would expect that it will land heads up 5 times, 50% of 10. However, if we only toss that coin a few times, we might be far away from the expected value. Perhaps we would get just 2 heads or 8 heads. That is possible. But if we were to flip the coin, say, 1,000 times or 10,000 times, we would get closer and closer to the real expected value. Recall the law of large numbers that we learned about in chapter 1, which states as the number of trials in a probability experiment increases, we get closer and closer to the actual mean or expected value. Mean and expected value are the same thing. Now, to find the expected value, we can use this formula here. We take each value of x, multiply it by its probability, and add up all those values. Let's take a look at example 4. We're revisiting the example from 4.1 with the researcher that records the number of times a patient rings for the nurse in a 12-hour shift, and we're given the distribution table. What is the expected value? Using this formula here, we take each value of x, multiply it by its probability, and then add it to each of those values multiplied by the probability. So, for instance, we're going to take 0 times 4 over 50, and we're going to add that to 1 times 8 over 50. And we're going to continue with this process for 2, 3, and 4. And we'll go ahead and solve for that. And we'll end up with 110 over 50, which is 2.2. So our expected value for the number of times a patient will ring the nurse would be 2.2 times during a 12-hour shift. On the next page, looking at example 5, we have a game where we're selecting a card from a 52-card deck and then tossing a fair coin. If the card is a face card and the coin lands on a head, you win $6. If it's a face card and you get a tails, you win $2. If it's not a face card, you lose $2, no matter what the coin shows. Let's go ahead and find the expected value for this game. And we'll go ahead and make our table where we have our random variable representing the net gain or loss and the probability of x. We have that we get a face card with a head, a face card with a tail, or we do not get a face card. It doesn't matter what we get on the flip of our coin. So if we do get a face card and a head, we will get $6. Face card and a tail, we'll get $2. But if we don't get a face card, we lose $2. So we'll use negative values here. Now we'll figure out our probability. The probability of getting a face card is 12 out of 52 times the probability of flipping a head is 1/2. probability of getting a face card and then a tail, again, will equal the same as the above. And the probability of getting not a face card is 40 out of 52. The probability of getting a head or tail is certain. It's 1 or 100%. Now, let's go ahead and find our expected value. We are going to take our net gain, multiply it by the probability, and then add it to each of these products. So we went ahead and wrote that down, and when we compute this, we'll get a negative value, which means we expect that we're going to lose about 62 cents every time we play this game. And that's rounded to the nearest cent. For part B, we're asked to explain this. And in other words, if you play this game repeatedly over a long string of games, you would expect to lose 62 cents per game on average. You shouldn't play this game to win money. Let's move on to our next page. Probability distributions also have a standard deviation. And we have our formula right here. Generally, though, we're going to use a calculator for our standard deviation, so you don't need to memorize this formula. However, we are going to show how it works here in example 6. Go ahead and read example 6 about Florida State University and its 14 statistics classes. For letter A, we're asked to find the average class size. And to find average, we will add up these values like so, and we would divide by the number of classes, and we'd have 70. In letter B, we're told space is available for 980 students. And we are going to select one student and random, and let our random variable be the size of the student's class. Define the PDF for X. So let's go ahead and make our probability distribution function again. So we'll go ahead and we'll draw our table, and then we'll fill in the appropriate probabilities beside each value. In letter C, we're asked to find the mean of X, which is the same as the expected value. Remember our symbol for mean, and we're going to go ahead and take each of our variables, multiply them by their probability, and add all of those up. And that will equal 980 over 14, which will give us 70. Lastly, for letter D, we're asked to find the standard deviation. I'm going to show you what it would look like if you do it by hand, but you won't be required in this class to find the standard deviation by hand. We'll use the calculator for that. And as you're doing these calculations, you'll likely begin to have an appreciation for your graphing calculator, which is able to perform these calculations quite quickly and save us a lot of time. And there we go. There's our standard deviation. And if you'll notice, that was our symbol for our population standard deviation. And that's the end of our video for section 4.2. I hope you found it helpful.